All right, well, we're going to finish chapter 9 today on epoxides. That's probably going to take us 20 minutes, 25 minutes. And then we'll dive into chapter 10, okay? So with epoxides, the idea is that the whole theme of chapter 9 was that OH minus and OR minus are terrible leaving groups. However, in the case of the epoxide, it's okay because if the group leaves, if this OR group leaves, you relieve a lot of ring strain. So the relief in ring strain pays for the opening of the epoxide, of the fact that an OR minus group is typically a bad leaving group. The mechanism of the reaction's SN2. It involves backside attack with inversion of configuration. Now, when you show backside attack on an epoxide, it is most convenient to draw an epoxide this way, with the oxygen and the two carbons in the three-membered ring all in the plane of the page. The substituents on carbons A and B are therefore dashes and wedges. But when you go to show nucleophilic attack with inversion of configuration from this perspective, the OR minus leaving group is here, and then the nucleophile is here on the opposite side of the molecule. And you show backside attack by having these two substituents, which were wedges, which was a wedge and a dash, but angled towards the bottom of the page, be now a wedge and a dash, but angled up towards the top of the page. That's how you show inversion from this perspective. You do not switch wedges and dashes in this perspective. You just tilt them from being towards the bottom of the page to being towards the top of the page. Normally, when you open an epoxide, the leaving group, which is a negatively charged oxygen, doesn't stay negatively charged permanently. Either you're using a protic solvent that can protonate that negatively charged oxygen after the fact, or you take care of that in aqueous workup of your reaction mixture. What I just said doesn't make a lot of sense to you until if you were to work in an organic lab or go take the Organic Lab 353, you would learn a little bit about what aqueous workup is. Effectively, we just add water to protonate the stuff that's negatively charged. The product of an epoxide has a nucleophile and an OH group on adjacent carbons. So anytime you see an OH group with an adjacent nucleophile, that is one bond away, that's an indicator that you could have made that molecule by opening up an epoxide. All right? Okay, so there are two key issues you need to be aware of for epoxide opening. One is stereospecificity, and the second is regioselectivity. So we're going to deal with both of those. Stereospecificity means, whoa, that was interesting. You also can't kneel in one of these. Come on. I guess Vader's belt was not meant for accessories. Huh. Oh, I think I actually broke the... What are we going to do about that? Yeah, all right, well. Somebody that's not me is going to have to fix that. If I just talk loud, can you hear me at the back? All right, we just not worry about the mic. Okay, so issue of stereospecificity is related to the fact that this mechanism is SN2, and therefore you are required to have backside attack with inversion of configuration. I mean, you've been learning about that for a while now, but it has some, it's useful to illustrate in the context of an epoxide. So When a reaction is stereospecific, if you change the stereochemistry of the starting material, you will get a different stereochemical outcome in the product. Let me illustrate that with an epoxide here. You've actually seen this before, I think, maybe on a problem set or an exam. This is a meso epoxide. It is not chiral. Carbons A and B are equal to each other. Maybe we'll call them, A and B is, let's just call them 1 and 2. We don't care. C1 is equal to C2 here, and there's a plane of symmetry that makes the molecule not chiral. I chose this example deliberately so that it would not matter whether we attack C1 or C2. Now, we're going to use a strong nucleophile. We'll use MEO-. Now, on a problem set that might be drawn as NaOMe with methanol as the solvent, but you have to realize that sodium is simply the counter ion and that MEO- is a strong nucleophile. We'll have that nucleophile attack either carbon 1 or 2, doesn't matter which, I'm choosing 1, they're identical to each other, to get the following product. Here is the OR- leaving group that left. Here is the OMe nucleophile that attacked. Notice that on carbon 2, I don't do anything to the stereochemistry, but on carbon 1, the methyl group, which was a wedge and angled towards the bottom of the page, is now angled towards the top of the page, and the hydrogen, which was a dash and angled towards the bottom of the page, is now still a dash but angled up towards the top of the page. That is how you show inversion of configuration. Then, afterwards, you pick up a proton from the solvent or during aqueous workup. In this case, if the solvent is methanol, you've got plenty of protons present, and your product is this. And if you want, we can redraw that product in a slightly different way. If I tip the carbon atoms down into the plane of the page, the 2 oxygens become wedges. All right? Now, I told you the starting material was not chiral, but it turns out that this product is chiral. And there's no chirality ex nihilo. You can't get it from nowhere. Go ahead.
I'm kind of confused on how the stereochemistry changed.
Yes, it has changed because these groups are pointing in a different direction. The issue you're experiencing is when you've seen inversion of configuration before, we've drawn it where the leaving group was a wedge or a dash, and when the nucleophile comes in, we've showed backside attack like this. We might also have shown that in this way. This is the exact same reaction. I think I got the stereochemistry wrong. Yeah, that'll work, maybe. You can also show inversion of configuration like this, where 1, 2, 3, yep. And it's all just a matter of perspective. Those two are the same thing. When you view inversion of configuration where your leaving group is at a wedge or a dash, then you show inversion by simply replacing the leaving group with the nucleophile and switching the configuration, dash to wedge and wedge to dash. When your leaving group is in the plane of the page, you show inversion of configuration by showing now the nucleophile replace the leaving group on the left side, and then everything else pops over. So those are two different ways to show the same thing.
Okay, is there a reason it goes like? Never mind, makes sense. It seems like the bond like
Yeah, don't worry about this bond here, which I've drawn in two different ways. That's a bond that's not that's a carbon that's rotating freely, and so, yeah, I could have kept it exactly the same or close to it if we wanted to. Yeah. Okay, so there's no chirality from nowhere. If you start with a non-chiral starting material, you have to, and you get a chiral product, you have to make the other enantiomer. Any guesses where that other enantiomer comes from? Yeah, how about attacking C2? If we attack C2, then I'm going to just skip ahead to the product. Attack at C2 will give us this product, which if we were to redraw, is the enantiomer of the product above. Okay. But notice we don't get any of the other potential diastereomers where one of these two would be a wedge and the other would be a dash. We only get these two enantiomers, and that's determined for us because we get backside attack. Now, if a reaction's really stereospecific, then if we make a change in the structure of the starting material, that ought to be reflected in the structure of the product. So let's now change the starting material. Let's now have our starting material be this chiral epoxide. Carbons 1 and 2 are still equal to each other, but this is just a single pure enantiomer. So let's show what would happen if we used the same MEO minus to open this epoxide. We'll show it attacking carbon 1. And that would give us, I'm skipping the protonation step afterwards. We're just going straight to that to save a little bit of time. This would be the product. If I were to redraw that a little bit, sorry, got to think for a minute. This OH would be a dash. Notice how that's a diastereomer of the product above. Notice that my two starting materials here were diastereomers. And notice that my products from above and below are also diastereomers. That's a hallmark of a stereospecific reaction. You start with a different diastereomer, you get a different diastereomer as a product. Now, what if we attacked at carbon 2? It just so happens if we attack at carbon 2, I'll draw the product that we would get. But it ends up being identical to the product above if you do the spatula pancake flip. You get the same thing. So from this starting epoxide, which was chiral, we get one chiral product. That's fine. And because our starting chiral epoxide was a diastereomer of the one we did above, the product is also a diastereomer of the products above. Yeah?
Pancake flip on the wedges and dashes?
Yeah, sorry.
Okay,
Thank you.
just making sure.
Yeah. Must be lack of oxygen from the mask addling my brain. All right. Okay, what else?
So if you have a chiral start, then you have a non-chiral product?
If you have a chiral starting material, can you get a non-chiral product? Yes, if you go through a non-chiral intermediate. So the classic example of that, and I can't think of one for the epoxide because the mechanism is SN2, but the classical example of that is if you have like a carbocation intermediate that's planar and achiral, even if your starting material was chiral, the chirality is lost, you get an intermediate, and then you can attack from either side. Yep. Okay, what else? Yeah.
When you have a chiral starting product and you open the epoxide, are you always going to get meso compounds in each other?
When you have a chiral starting material and you open the epoxide,
Second example, is it always like
This-
if you had a different chiral epoxide, would it also be meso compounds?
so these aren't meso compounds. This is still chiral, but they just happen to be the same thing. Now, whether it's a chance to have a meso compound or not, whether it's chiral or not, is really going to depend on the epoxide that you're dealing with. So I would say rather than try to memorize rules about the meso epoxide leads to this, a chiral, just do what you know how to do, which is backside attack with an SN2 reaction, and that should do it. Okay? So that's other questions or follow-up questions? Okay, that's stereospecificity. Let's now do regioselectivity. And we'll actually do stereospecificity at the same time. So here is a chiral epoxide. This one's difficult to draw, and because of that, we're drawing the six-membered ring in the plane of the page. We're drawing the epoxide as being oxygen attached to both carbons 1 and 2 via a wedge, and then remember wedges and dashes point in roughly the same direction, just one is a wedge and the other is a dash. So I have to put the other two groups here. We'll say carbon 2 has a methyl group and carbon 1 has a hydrogen. When you show backside attack from this perspective, you're just going to do the same thing we've always done with dashes or wedges with leaving groups. There are two options for opening up epoxides. The one is with a good nucleophile. And for a good nucleophile, the mechanism is straight up SN2. As you know, you get backside attack and you get inversion of configuration. All of that stereospecificity, but the other thing you need to know about SN2 is steric factors are important. So if I were to have a good nucleophile attack this epoxide from the back side, which of these two carbons, 1 or 2, do you think would be preferentially attacked? 1. Why is that? Less sterically hindered. Yeah, steric factors are dominant here. The epoxide, the nucleophile will attack the less hindered carbon of the epoxide. So we're going to do backside attack on carbon 2, and the leaving group's going to leave. I'm going to skip the subsequent protonation step. I'm going to show MEO being at carbon 1 as a dash because we've got inversion of configuration. Then at carbon 2, I'm going to show an OH group. That was the leaving group from my epoxide, and MEO is my nucleophile. The methyl group on carbon 2 stays where it always was. The proton on carbon 1 ends up being up because of inversion of stereochemical configuration. And so this is the product. The nucleophile ends up at the less substituted carbon, and the OH of the epoxide ends up at the more substituted carbon. And again, that's purely because sterics dominate. Okay? Questions about that? All right, let's now have a second option, which is opening an epoxide with a weak nucleophile, but using an acid to protonate the oxygen first. Generally, we've seen that weak nucleophiles don't do SN2. So, but with epoxides, they can, as long as you protonate the oxygen first. So, let's imagine that we take the same epoxide. We had a methyl group here. And let's imagine that we use methanol, but we add a little bit of acid. It turns out we will only need a catalytic amount of acid. So I could write methanol and HA. Another way to write this same thing would be to write the conjugate acid of methanol, which is what you get actually when you put HA in methanol. Your text will also write this as MEOH with H+. Not that you can go out and buy H+, which you can't, but that's their way of saying, hey, I'm adding an acid, but I'm too lazy to tell you what it was. Okay, so when you add the acid, the first thing that happens is methanol, the oxygen of the epoxide picks up a proton. And you get this oxonium ion, where now the epoxide oxygen is an even better leaving group because it could leave as a neutral ROH group. Okay, now what happens next, you're going to love, because actually you're going to hate, because the mechanism is an SN1-like SN2 reaction. What does that even mean? Okay, first, we still get backside attack, and we still get inversion of configuration, always. But the weak nucleophile attacks the less substituted carbon. No, I said that exactly wrong. Scratch that. The weak nucleophile attacks the more substituted carbon. In other words, your product would show the methoxy group here. This is what you would get immediately after the methoxy group attacked, and then the OH over here on carbon 1. Methanol is your nucleophile. This is your leaving group. So do you see how that is a different regioisomer than we did above? And then because this reaction is catalytic in acid, we remove the proton from what used to be our nucleophile, and that gets us to this product, which I'm not going to redraw. I'm just going to paste it. Dun, dun, dun. All right. Do you see how the product below is a regioisomer of the product above. Yeah.
So you're saying it's SN1-like, not because there's an intermediate or more than one product, just because it attacks the more substituted.
Yeah, so we need to explain why it attacks the more substituted carbon. So to set this up, let's zoom in on that intermediate. You see a positive formal charge on the oxygen, but you know that oxygen's more electronegative than carbon. So it makes sense that most of that positive charge should be shared with the adjacent carbons. Now, if I look at carbons 1 and 2, I have a choice. Do I share the positive charge evenly between the two carbons, or do I put it more on one than the other? And the idea is if I put it more on one than the other, I should put it in a place where it's more stable. Well, you know something about carbocation stability, which is what? On what types of carbons are carbocations more stable? More substituted ones, right? So it makes sense that the partial positive charge should be shared with the more substituted carbon. So why does the weak nucleophile attack the more substituted carbon? Because that's where the most partial positive charge is. Why is that? Because it's more stable there. Because the delta plus is more stable on the more substituted carbon. We're giving you practice for being parents of a 3-year-old. Why? Because of sigma to p hyperconjugation, which allows electron density to spread out. Also, you can think of inductive donation of electron density by adjacent alkyl groups. Why? Well, actually, hyperconjugation is an explanation. There's no why to hyperconjugation. Why? Stop it. Actually, at that point, you distract the 3-year-old with a popsicle or something. Okay, so partial positive charge builds up on the more substituted carbon because it's more stable. Now, this should still give some of you heartburn because I'm proposing an SN2 reaction at a tertiary carbon. And you've been told not to do that. There's a reason it can happen here, and this gets into what we mean by SN1-like. If we zoom in to the transition state, and I'm going to put, let's see, this is going to be carbon 1, which was less substituted. This is going to be carbon 2, which was more substituted. I'm going to draw the epoxide in a little bit different way. Hopefully that's okay. The R1, the R primes are the ring substituents. And if I got the stereochemistry wrong, it's not going to have any consequences for us here. The oxygen will start to lean away from the more substituted carbon, and the bond between carbon and oxygen will lengthen, and that creates the buildup of positive charge on carbon 2. As that bond is leaving, carbon 2 rehybridizes, flattens out, and becomes a little bit more trigonal planar, a little bit less sp3 hybridized, a little bit more trigonal planar. That opens up space for the nucleophile to come in and attack. So here's our MEO nucleophile. And we'll use the double dagger in the bracket to indicate that this is a transition state. But yeah, the idea is that the more substituted carbon 2 flattens out a little bit like you would expect in an SN1 reaction. so that it's easier for the nucleophile to attack. Now, this is what we mean by SN1 like SN2. The carbon flattens out, it gets some positive charge, the nucleophile can attack it even though it's tertiary. That's the way it's SN1 like. How is it still SN2? Because the leaving group is still blocking this face of the electrophile, so you still get backside attack. Okay? So when you're using an acid to protonate the epoxide first, then you get backside attack with inversion of configuration, but at the more substituted carbon. Okay? Questions on that? So I need to post problem set 9. I'll do that today once I get out of this Darth Vader costume. Zipper's in the back. I really hope I don't have to go to the bathroom before I get out of the costume. So stop drinking water, right? Yeah. That was a rookie mistake. Any senator that's filibustered for an hour knows not to drink water, but filibustered for an hour, I mean 24 hours, whatever. Anyway, well, okay, I'll post problem set 9. There will be epoxide problems on that where you can practice this, practice the stereochemical issues, practice the regiochemical issues. Yeah?
Can we also get the keys for problem set 8?
Yes, they are posted.
Checked like an hour ago. And
Did you? Maybe I forgot to press save. I'll post them if I haven't.
Thank you.
Yep. Now, oh, by the way, some of you have expressed concern. The number on the problem set, it reflects the week of class that we're on and not the chapter. So you'll notice that last week, problem set 8, we were doing chapter 9. That maybe drove a few of you crazy, and I'm sorry about that. But we just go with it. It'll be okay. All right, so now that concludes chapter 9. We need to go to chapter 10. There are five new reactions in chapter 10. 10 of them, 10 if you count the difference between reacting with an alkene versus an alkyne. We're going to do some stuff with alkynes, but not a ton. However, there's really only one or maybe two reactions in chapter 10. If you can follow the patterns that are going on and see similarities. The main theme of chapter 10 is going to be a carbon-carbon pi bond as the HOMO of a nucleophile attacking an electrophile. Your text will call this electrophilic addition to an alkene, which is fine, but it's the alkene that's the nucleophile, and its pi bond is going to be the thing that's doing the attacking. Another word for alkene, if your nose is plugged and you don't want to sound nasally, is olefin. That's from the petroleum industry. I might say olefin when I get sick of saying alkene. We will also see some reactions of alkynes. And then the electrophiles here are going to be several different things. So the variation you're going to see is going to be in the electrophile, but the nucleophile is basically always going to be a pi bond in chapter 10. So let's just review what an alkene is. Okay. Here is a 6-membered ring containing a pi bond, and there's an alkene. I've chosen this example deliberately. We'll explain why a little bit later. But if you were to draw the pi bond, the pi bonding orbital, it would have one large lobe that's above the plane of the sigma bonds. The sigma bonds are all drawn in the plane of the page. And then another equal-sized lobe below the plane of the page. And what you have to understand is that an alkene has a top face and a bottom face. So, unlike the nucleophiles you've seen so far, which in chapters 7 through 9 were all just molecules with lone pairs on a single atom, and that was usually negatively charged. With an alkene, the HOMO is shared between two atoms, and not only that, but it's also in two places at once. It's above those two atoms and below those two atoms. So you've never had to deal with, well, which side of a nucleophile does the attacking? You will have to deal with that now, because the pi bond has a top face and a bottom face. And so you will need to consider the nucleophile reacting from either face. Both faces are identical. There's no difference, and the pair of electrons is equally shared on both faces. So you have to think of, when the pi bond attacks as a nucleophile, you have to think of attack from the top face or the bottom face. And that needs to be, you need to think of that as happening with about 50-50 frequency. Okay? Has to be, because they're identical. The second issue you're going to have to deal with is when those two electrons in the pi bond attack some electrophile, you're going to form a new sigma bond with the electrophile, but the two atoms of the pi bond can't be sigma bonded to the same thing at once with just two pairs, with just two electrons. So one atom, one carbon of the alkene gets a sigma bond with whatever the electrophile was. The other gets a positive charge. And you're going to have to figure out which. Okay? So let's actually deal with that. We'll deal with both of these issues in the same step. Now I'm going to change our starting material just a little bit. I'm going to replace hydrogen with the letter D. I'm doing this on purpose because it's going to allow us to illustrate the nucleophile attacking from its top face versus its bottom face. D equals deuterium. Deut is, I think, Greek for two. It's the same root word that's Deuteronomy, which is a second stating of the law in the Old Testament. Deuterium means two in the nucleus instead of one. It is an isotope of hydrogen, but it has a neutron, whereas a hydrogen nucleus doesn't. It is chemically indistinguishable to hydrogen, chemically equal to hydrogen, but you can tell the difference between the two of them through some fairly simple experiments. So it's going to be just like a hydrogen, only it's got a label on it that we can detect. Okay? We've labeled things before. We've called that blue hydrogen and pink hydrogen. This is one way chemically you can label a hydrogen. All right. So let's react the alkene with the first electrophile, which is going to be an acid. Now, there are two reactions that you'll learn in chapter 10 that have to do with this. The first is called hydrohalogenation, in which HA equals like HCl or HBr. The second is hydration, where HA equals H3O plus. Often that will be in like sulfuric acid or something like that. Those are two reactions you can learn about and memorize independently, but I think that would be unwise because they're basically the same reaction. The only difference is what's the conjugate base. Okay? So, HOMO of the nucleophile attacks LUMO of the electrophile. The LUMO of the electrophile is the HA sigma star. So pi bond attacks hydrogen. We break the HA bond. Now we have to decide who gets the hydrogen and who gets the positive charge. Which do you think? One or two? C1 should get which? The plus. Why? More substituted, carbocations are more stable. Why? Hyperconjugation. Why? And then the answer to that is squirrel.
God made it that way.
Yeah. Just distraction at that point. So here is, we're going to put the hydrogen at carbon 2 so that the positive charge can be on carbon 1 where it's more stable. The hydrogen can have been added to the top face of the alkene or the bottom face of the alkene with equal frequency. It has to be that way because the top face and the bottom face of the alkene are identical. So we've just answered the question, which gets the electrophile? The less substituted carbon gets the new sigma bond with whatever the electrophile is, so that the more substituted carbon has the positive charge where it's more stable. Your text summarizes all of that as the Markovnikov rule. I'm not big in memorizing names of dead people and the rules associated with them, but you'll see that language in organic chemistry texts from time to time. We'll call this Markovnikov regioselectivity because we get specifically the isomer where the hydrogen goes on less substituted carbon 2. All right, now what happens is basically we're back in SN1 territory. The first step is the only new step. The second step, your intermediate, is a carbocation. What are you going to do with that carbocation? What do you think happens? You have a negatively charged conjugate base, which is now your nucleophile. What is the LUMO of your carbocation? The empty p orbital. And if you were to draw that, you would see that it is both above and below the plane of the page, equally distributed on either side. So your nucleophile can attack the positive charge either from above or below. That means for the carbocation on the left, you have two options. The first is for the nucleophile, whatever it was, to be up. And the second is for the nucleophile, whatever it was, to be a dash rather than a wedge. Of course, on carbon 2, nothing changes. That stereochemistry was set in the previous step, where D equals deuterium. Okay? Do you see that that second step of the reaction is really just the second step of an SN1 reaction? So this isn't totally new, it's just one new thing. Now we can do the same thing on the other carbocation from above or below, and we will likewise get two different products, one in which the nucleophile that attacked, the conjugate base, is up, and the other where that nucleophile that attacked the conjugate base of our acid is down. Of course, the other carbon stays the same. It has to, because its stereochemistry was set in the previous step. Okay? So as you can see in this reaction, we have two different steps of nucleophile attacking electrophile. In the first step, I will use, I don't know what color I want to use, blue for the electrophile, hydrogen, and that can be added from above or below. And in the second step, green for my, actually, we'll use purple, because purple is what we use for nucleophiles. In the second step, the conjugate base of my acid acts as the nucleophile, and it adds to the positive charge from either above or below. Okay, questions about that? Why did the D move there? Who did that? That was me. Okay, go ahead.
Just a quick question. So if we were to have rearrangement though available, would that give two other steps?
So one question is, if carbocation rearrangement were possible, would it happen here? Probably. Can I think of a good example of that? Not off the top of my head. Yes? Right, so a good question is here, do you need the dashes or wedges because you have 4 products with all 4 possible stereochemical configurations? I did it on purpose for a reason I will discuss next time, but no, a correct answer could just use straight lines and just one thing. Okay, well, may the force be with you. Have a great Halloween. I will see you Monday.